Yeah, so this week we have Hannah Cairo from UC Berkeley, who's going to give a talk about the Mizohata-Takeuchi conjecture. Yep.
All right, hello everybody, and thanks for having me. So before I get started, I just want to say like this talk is meant to serve two purposes. Um, I guess first I would like it to be at the general analysis level. So, if you come here from like some other area of analysis and you're not too familiar with like restriction theory, there should be something that you can take away from it. Now, the other thing is that my recent preprint does have like a few like techniques that are like not used in this area, and I would like to go into a certain amount of detail in them, just because I think that these techniques can be applied to other problems in restriction theory. So I'm thinking that like for the first part, I can talk about some stuff that probably a few of you from harmonic analysis will already know, and then after that we can get into like the this new stuff that's actually from my paper. Okay, so first things first, just like what do we think of when we think of like Fourier transforms and stuff? So I guess there's sort of like these guiding principles that I feel like I would say that, like in Fourier analysis, we like decompose any like function into like a bunch of like waves, and each wave has like these different frequencies, and then like we look at the structure of the frequencies that it's made of, and this is supposed to tell us something about the function that we get. So on the left we have like an approximation to, I guess, the characteristic function on like some circle, and then we take a Fourier transform, and then we get like some sort of Bessel function thing. So we can see that we can start with something very simple and end up with something very complicated. Um, okay. So in Fourier restriction theory, we wonder, what if we only use like certain frequencies for our waves? And in particular, like, well, I guess usually when we say Fourier restriction theory, I think that oftentimes we're restricting to like a hypersurface or something like that. Technically, it is also meaningful to talk about restrictions to other sets. But for now, we're just going to be talking about like hypersurfaces. So the idea is that we take some function and we need to say like, okay, what happens if we consider only the frequencies that like lie on this hypersurface? So here I have like this paraboloid thing, and there's like these sections of it, and those are where all the frequencies are going to come from. So like if we imagine like if we take the function to be like one on those pink regions, if we take the Fourier transform of that, then we wonder like what kind of function are we going to get? And this is useful in, for example, PDE theory, because, for example, if you're looking at solutions to like the Schrödinger equation, the homogeneous Schrödinger equation, then like all the frequencies are going to like lie on this paraboloid. And it's useful to know like how do these different frequencies interact? What kind of interference patterns do we get? It's also useful in analytic number theory, and it also is just useful, just like, I don't know, it has some intrinsic value in harmonic analysis because I guess it is an interesting question in its own right. Like, what happens when you take the Fourier transform of something and it concentrates on some hypersurface? Um, yeah. So the first thing is that the name of the field is called like restriction theory, but the first thing that we do is we actually talk about the extensions, which is like sort of the dual. So it's like originally we might say like take a function, take the Fourier transform and restrict that to this hypersurface. But by duality arguments, these are really just the same as taking some function supported on a hypersurface and then taking a Fourier transform of that. So that's what we can be thinking about for now. Okay, so there's some notation, I guess. If we take some function that's supported on a hypersurface and we take the Fourier transform, technically it's not actually the Fourier transform, because if you just take a function that's like, zero away from like a set of measures zero, then like it doesn't make sense to just like integrate that, right? So what we do is we multiply our function by like the surface measure, and then we integrate that. So that's like a maybe more of like a technical thing. If you don't come from like whatever, if you prefer to think of it as just taking a function, you can also imagine it as like imagine it's in a very thin neighborhood around this hypersurface, and then like you send that neighborhood to zero and see what happens, and stuff like that. Um, so this is just like generally like the and like an overview sort of like the type of things that we like to study in restriction theory. So then, you know, mathematicians, like one of the first things we like to do is ask like how big are these things that we deal with. So if we're looking at this operator, right, then we want to look at like what kind of mapping properties does it have. So like if we take a function f that's like in some LQ space and we take a Fourier transform, then we wonder what kind of LP spaces it's in. And in harmonic analysis, this is a natural notion of like size, sort of. So for example, like Plancherel is not going to hold in this case because, if the function, if we take a Fourier transform or something and we get something L2, well, that just means that the original thing we started with was L2. And you can show that it's not L2 because like you're multiplying it by the surface measure and all that. So classically, we have like the Stein-Tomas theorem. If you start out with a function in L2 and then you take the extension operator, then you'll get something in LP, where P is greater than or equal to 6 in dimension 2. And, then there's also this important conjecture. I wrote it, I wrote Stein's name there, but I think there were a lot of people involved in the 1970s. I was not around then, but this is like the sort of like a central conjecture in the field, the restriction conjecture. And it's sort of like if we, technically like the exponent here should be a little bit different, but you can like use like dyadic pigeonholing arguments and stuff like that. So like you can sort of imagine that if you take like just a bounded function, you take like the extension operator, then we wonder what LP spaces it's in. And the conjecture is like this number here, which is um like 4 in dimension 2 and 3 in dimension 3, and then like not integers after that. In dimension 2, it was solved in the 70s. The argument in dimension 2 is simpler than anything else, and we actually don't know how to do it in dimension 3. I I think the best result, if I hope somebody here knows the actual fraction, but I think it's like in dimension 3, I think the best we have is like when p is greater than like 40/13 or something like that, which is slightly larger than 3. Um, the exact exponent might be something else because I don't really remember those. But this is like first question we ask. And second question that we wonder is what is the shape of our extension operator? So the idea is that if we take a function, all of whose frequencies lie on this hypersurface, then we expect it's not just going to have some size restriction, but it's also going to have some sort of shape restriction. Okay, and then for now, for a little bit, I'm just gonna talk about the wave packet decomposition. So if you like study restriction theory, then I hope you don't get too bored. But the idea is that we hope that the extension operator is going to concentrate on like tubes. And the reason why is because of the uncertainty principle. So how I usually like to explain this is that imagine that you have like a wave and all of its frequencies are like bounded by, in this case, some r. In this case, all of the wavelengths we can say are at least 1 over r, right? So you can imagine that like, you know, the distance that to travel like a full cycle is going to be like at most 1, like at least 1 over r. And so we expect that the function is not going to change very much if we only go by like half a wavelength, right? So really what I'm saying is that if all of the frequencies are bounded, then the function is not going to change like very much if we're moving like less than that corresponding wavelength. And this is quantified in this way. If we start out with a set with like a function g, which we can think of as like some frequencies that we're going to use to build a function g hat, then if we're only using frequencies that are small, then, or sorry, only frequencies that are like within this set, which might not be too small, but whatever, then the Fourier transform should be concentrated on intervals with this width. This result generalizes to higher dimensions. I guess, if it's going to be like concentrated on like this, with A and then with B and then with C, then the Fourier transform is going to be locally constant or essentially constant on like these on like boxes with these dimensions, 1 over A, 1 over B, and 1 over C. Okay. How do we use this here? First it's nice to like draw a picture of this. If we're starting off with a set of frequencies here, what we're really just saying is that it has to be constant along these. Now, you can imagine that why that is because this one is a bunch of like, this one is like all these frequencies here. So the possible wavelengths, like the wavelengths could be like very like small, right? So there's like this thin width here. On the other hand, um, like this distance here is fairly small, so we're dealing with small frequencies and large wavelengths. And so like it's going to be essentially constant along these things. Um, so basically like this is this is like the idea behind the wave packet decomposition. You can imagine that here we have all of these different things here, and we can imagine those are like boxes, all of those, little sections on our paraboloid. And so we can sort of like break our function down into these pieces and like look at how they interact. So here we have like a picture of that happening in 2 dimensions or in 1 plus 1 dimensions. So we're starting off with our surface sigma, and then we break it into these pieces. And the idea is that the Fourier transform on each of these things should concentrate on tubes moving in this direction. Now, the reason why the wave packet decomposition is hard is because remember that this is only a box centered at the origin. If we were to translate the box, then we're introducing all these oscillations, and so like the boxes that are not centered at the origin are going to come with a lot of oscillations. And so you can imagine that we're going to get like all of these different tubes sort of that are like meeting each other at different angles, and each one comes with like different oscillations, and like figuring out how to bound things like that can get very hard very quickly. Um, so yeah, this is sort of like the idea of the wave packet decomposition. If I guess you got lost somewhere along here, you can come back. Um, we have like in summary this principle that if we take the extension operator, it should concentrate on these tubes. So then how do we like quantify what we might expect here? So what we can do is we can take like a weighted estimate. So this is just like an L2 norm, except we're taking a weight, some W. And the idea is that we want this to like be bounded by the original like thing. So we're sort of saying that we want the extension operator to be a bounded operator from L2 of like a surface measure to like L2 of Rn with some weight W. And the operator norm should be controlled by some measure of size of our weight. And the idea is that if it concentrates on tubes, you can sort of imagine that like this quantity here should tell us the total a number of like tubes, the total like tube mass that we have. Um, because this is like counting like, you can break it down like, the different like take the Fourier transform of like frequencies that are like all in like one small part, and then you're gonna like see a lot of translations of like these tubes, and like the idea is this should tell us the total amount of like tube mass that we have. And this quantity tells us the total amount that a single tube can contribute. So this is saying that a single tube is going to look like more or less like a line. And the idea is that we want to look at how much a single tube can contribute to a weighted estimate. If W was, say, the entire, like 1 on the entire, like Rn, then we would expect this estimate to like not hold because this, or maybe estimate does hold because this thing is going to be, oops, uh, hang on, I have my eraser selected instead of my laser, because this quantity is going to be like infinite in that case, because a single tube is going to be like contributing a lot of mass to this estimate here. So this conjecture came about, I guess. Takeuchi was originally studying like PDEs and conjectured like some sufficient condition for well-posedness of like first order perturbations to the Schrodinger equation. And then Mizohata came along and pointed out that this step in his proof actually does not necessarily follow. And then like, I guess a few years later, there was a paper by Barcelo, Ruiz, and Vega. I don't know if any of them are here. Um, I don't Well, it would take me too long to scroll through the participants list. But that was a while ago in like I think the 90s, and then this is like what made the conjecture like in its current form. Alrighty. So if you got bored anywhere there because you already like know about this, or if like maybe some of the things that I said, you maybe got lost somewhere, you can come back around now. Because now we're just gonna like start fresh and sorry, not start fresh, because I have one more slide. Okay. So my like recent theorem is that the conjecture is actually false, and specifically that the error that we get, like that thing, the less than or equal to sign. This sign, by the way, if like it just means less than or equal to like times a constant. Um, so I said that the constant there actually grows with a logarithmic factor. So um, if our weight W is supported inside a ball, then there's an error that grows with at least a logarithmic factor. So that's like what I plan on talking about today. And I'd like to like sort of get into a few of like the details of the argument, just to like explore some of the ideas that are like not usually used here. Okay, so I apologize for my remark on the last slide, but if you did get lost, then now's the time when you can come back. Um, Now we can actually talk about how we can like prove this. Okay, so I want to like step by step digest each of the things here. So like I want to talk a little bit about first I'm going to talk um in like section 3 on about like the left thing, and then section 4 I'm going to talk about like this stuff, and then we're going to put everything together. Okay, so first things first is this quantity here looks hard to deal with. Um, right, it's like just, in general, weighted estimates tend to be hard. But if it was the square of something, then it's the L2 norm of something, and then hopefully we can like use Pointryel. So maybe this is going to be unmotivated at first, but the idea is that we want to write everything in frequency space. Um, and then hopefully that can like allow us to look at it um, through like a different lens, I guess. Um, So I hope this isn't unmotivated, but we can set our weight to be the square of some function, h, and then let's say this is the square of like the Fourier transform of h. Um, and then this should like allow us to rewrite this. Before we get into that, I just want to talk a little bit about the uncertainty principle again. If W is supported in the ball of radius r, then we want to know like what does this say about h? um, it will say that h is like going to be locally constant at scale r to the -1, because if all our frequencies lie in like this ball, then all of our wavelengths like are going to be greater than r to the -1/2. So h should be like h and w should all be like constant at this scale. Okay, so if you forgot what the equation at the top said, don't worry, we will like recall it when we need it. Um, but for now, like what we should say is that like if h we assume to be real and also non-negative, by the way, this is a bit of like a lot of assumptions, but we can actually still get a counterexample if we assume these things. But if we assume that h is real and non-negative, then this locally constant principle allows us to say that it's more or less a collection of these balls supported like it, this collection of r to the -1 balls, right? Because like, you know, I guess if it's locally constant at scale or inverse, then like you can just ask for like the value on all these balls, and like we're just gonna assume that it's 0 on most of them and then it's 1 on some of them. Um, okay, so then it's also convenient to have an L1 normalization, as we'll see later. Um, so this is like the definition of H that we can like be working with, I guess. So so far what we've done is we've written a weight as the square of the Fourier transform of something, and this is supposed to help us rewrite this. And we also said that since we are localizing to like this ball of radius r, we can choose h to be something that looks like this, sort of. Okay, so then just to give you like a sort of overview of, I guess, where I'm going with this, in section 3, I want to understand how to write this thing, and then in section 4, we can analyze this. And then later on we can like put everything together. Okay, so then if I lost you at some point, I think that this is like an area where we can like sort of come back. Um, we are just now trying to like analyze this term here on the left, and we can forget about like everything else that we've done. Um, so I guess the reason why we set W equal to this was, oops, switch to my eraser again by accident. The reason why we set W equal to this is so that we could write this as an L2 norm. And that's all I've done here, right? So I'm taking this EF and we're taking EF squared times W, which is EF squared times H hat squared, and we're integrating the square of the product. And, if we take like the Fourier transform of the product, then we just get a convolution. And sort of like the principle, I guess one of the like principles that like we should be working with is that we should not be afraid of convolutions. And I guess I feel like in general, convolutions, like dealing with the convolutions can make things on the Fourier side a bit more complicated, but I think that we can deal with it. So yeah. Um, so that's like basically all I've done so far. We're looking at the L2 norm of this convolution. And then we just want to like look at what does this L2 norm look like. So um we can again imagine that F is given as a collection of unit L1 masses. This is just a convenient normalization to be dealing with. Just imagine that everything is like a collection of L1 masses. H is a collection of like unit L1 masses, and F is a collection of unit L1 masses. And this will make it easy to deal with convolutions. So here I've drawn like the picture from before. So like we should imagine F is like, it has some mass over there, it has some mass over there, it has some mass over there. And instead of like taking the Fourier transform and then dealing with all these weird interference patterns, we want to handle everything on, the Fourier side, um, like before we take the Fourier transform, because this way we can deal with everything in terms of like vector addition and like convolutions and stuff that we know how to do. Um, that's all this one is saying. This is just saying that it's a collection of unit masses. There is a different exponent here. Oops. That is supposed to be an n, not a d, because here I have n as my dimension, not d. Okay. So then we have also like the 1 plus 1 dimensional case. We can imagine that F is like a collection of these like unit masses over here. And we want to examine like what does the convolution look like. Okay. So first, this is like, remember what H looks like, and this is like what F looks like. So what happens when we take like one sort of set and we want to like convolving a function that's like one on some set with like, characteristic function on another set is the same as sort of just like pretty much just adding those two sets together. Um, so we should sort of imagine that like for each point in F, we're copying like this picture and we copy that and paste it by like shifting it in some direction. So like we're taking this set and then we like copy paste it in all of these different directions, where the direction is determined by like these points in our set that determines F. Yeah. So that's sort of like the intuition that we should have. So over here on the left, I've taken this picture of H, and I copied and pasted it. There's like two over here that you can see, and then there's one over here. So we should just imagine that we're picking the set up and we're copying and pasting it everywhere. Okay, and if you remember from before, we're finding a counterexample, we're trying to maximize this. So if we only have so many like green points and so many pink points, so many pink like points that we're going to translate it by, and we want this to like have a very large L2 norm, well, we have like a fixed amount of mass we're dealing with because we have like whatever, so many green points and so many pink points. There's only so much mass we have. And if we want to maximize the L2 norm, we want this mass to be concentrated on smaller sets. So the idea is like if when we pick up Q and we like copy paste it somewhere else, we want it to land on like Q mostly. So one way that this is achieved is, for example, if you take like, I don't know, a grid, just imagine like a 10 by 10 grid in the plane. You pick it up and you like translate it by a bit and then you set it back down, and then it's like you can get it to land pretty much on itself if you translate it in like, along these certain like lattice vectors, right? So that's like the idea that we should have in our mind. We should imagine that this is somehow secretly some sort of lattice. And so we can pick it up and like copy paste it and like put it back down on itself, and we're going to get a lot of overlap. So we can quantify this like this. So if for every like green point, I want like, or maybe I can do this differently. So we pick a green point, um, like, and then I'm just going to say pick a pink point at random and translate it by that. So it's sort of like maybe we're starting with this point and then we pick like a random pink direction to translate it by, say like this direction. And I want to say that like at least 10% of the time, it's still going to be in P. So like we maybe are over here. So then this one says, okay, I'm going to go pick like these random points from like these random pink directions to go in. And I'm going to go, okay, well there it worked. And then like maybe there it didn't work. And then there it does work. But it's like at least 10% of the time I want it to like land on itself. So at this point, this is like a combinatorics question. Um, we should be wondering like we're taking this set of green points, and if it lands on itself at least like 10% of the time, then basically the idea is that this should be like all like concentrating on the original set. And if you work out the combinatorics, then you'll get that like, we have like it's concentrating on a set of size Q, and we have QP things, right? So if we have QP masses and it's concentrated on a set of size Q, then we're gonna have an average of like P stacked on top of each point. And so the L2 is going to be like P squared. So I can say that again, like if we are picking this thing up and we translate it most of the time, or 10% is not most of the time, but it's close enough. It like almost most of the time lands on itself. Then we're just taking P copies of this set and it like lands on top of itself and it's like sort of stacking up. You can imagine that like stacking up, and we're like, we have these like tall towers of like the points that we start out with. And in our set. Um, and if they're going to be like of height P. And so if we want to take an L2 norm, then we go to the square. So the square of the height is like P squared, and we have Q total like towers. And so we expect the total L2 norm squared to be like Q times P squared. And then we also pick up a normalization factor because we're converting from an L1 norm to an L2 norm. You can ignore these normalization factors because they're all going to disappear in the end. Okay, so if you got lost somewhere in part 3, we have a little summary. Um, remember that at the beginning, we were trying to analyze this quantity, and what we found is that if this condition is satisfied, then we can prove this estimate. And this is some normalization factor that we don't care about, and this is just like the real thing. And then we can forget about this until like the end. Alrighty, and if you remember from before, that was only the left-hand side of our equation. I would also like to talk a little bit about how to write the right-hand side. So remember that what we did was we took a weight and we're looking at like if we integrate it along a line, then how much like do we get? And this question is going to be a little bit harder because we set our weight equal to like this weird thing, but it's still doable. The idea is that we should not be afraid of convolutions. Um, okay, so this is classical. If we're looking at the integral of a function along a line, the only frequencies that are going to contribute to it are going to be perpendicular to like that line. And the reason why is because like if it's not perpendicular to that line, then we're going to end up with a lot of like oscillation that's going to integrate to 0 if we're integrating along a line. So this is formalized as the projection slice theorem. which I guess is like, technically I think the projection slice theorem is a more general theorem than this, but um, the idea is that the only like frequencies that are going to contribute to this quantity, looks like I ended up with an extra supremum there for some reason, are going to be perpendicular to L. So we can imagine that this is like some line here, and this line is in the direction nu, and this plane is the perpendicular plane to nu. So you can imagine if we have a frequency that's like over here, then this frequency is going to be constant along like this line. And so those are going to be the only ones that matter. We can formalize this as, if we want to take the integral of this thing, what do? Well, we take the inverse Fourier transform, we restrict that to this plane. We sort of like, you take the inverse Fourier transform, we're asking like what frequencies this function is made of, and then we like delete all of the frequencies that do not lie on this plane. Um, and then we take another Fourier transform. So that's all we're doing here. We're just deleting all of the frequencies that are going to oscillate on this line. That's what we should think of this operator as. Okay. Next slide, I think is, okay, no. Okay. So if we want to take the supremum over all possible lines, because remember we were looking for like the worst possible case, um, we can take first the supremum over all like directions, right? And then we can take the supremum over all possible places that line is going to meet this plane. And um, and the idea is that if we're taking the supremum of this quantity in Z, that is just an L infinity norm. Right? Because this is some function of Z. When looking for the maximizer in Z, that's just an L infinity norm. And if we're looking at the L infinity norm of the Fourier transform of something, that is going to be bounded by like the L1 norm of the thing we're taking the Fourier transform of. That's just like Hausdorff-Young, or I guess it's not Hausdorff-Young technically, because Hausdorff-Young is like once people did interpolation and stuff. So it's just like you write out the integral and it works, I guess. But yeah, this is so far like what we have. If you look at the paper, technically I think I worked this out for more general LP norms, but I think in for now we're like, for the purposes that we'll need it for later, we only need the infinity case. Um okay. Okay, so like sort of to summarize, we use the projection slice theorem, and what we're asking is like, really what we're looking at is like how much mass from like W is going to like concentrate on a single like plane. So we're like, if we take some plane that passes through the origin, we're looking for how much mass concentrates on that plane. And by the projection slice theorem, this should be equivalent to saying something about lines. So how do we estimate this? How do we look at the total amount of mass? This is where things get a little bit, this is the thing from last slide, I think, by the way. This is where things get a little bit complicated since we chose a weird weight. Um, I've introduced an intermediate K. So we take like H, we take the Fourier transform, and then we take the norm squared. So then this is going to mean that like W is equal to K times K bar. And so Fourier transform of the product of two things is going to be the convolution. So in summary, like inverse Fourier transform of W should be given as a convolution between two H's. And technically we had that complex conjugate there, which is going to mean technically we're like, if we take the Fourier transform of a complex conjugate, we have this extra reflection thing. So like technically this is H convolved with H tilde, where H tilde is just like sort of the reflection. And I've also gotten rid of all of the complex conjugation because remember that we decided that H was going to be real. So in summary, if you got lost somewhere in there, we were looking to bound this quantity, and we've bounded this quantity in terms of this quantity here. And remember, we should not be like scared of convolutions. So hopefully we can like figure out how to deal with these convolutions. So now we have to look at this. Okay. remember that H is a collection of unit masses. I'm gonna say that the convolution, remember, that's like if we take a set and then we like add it to another set, right? And if we think of H as like a set, then H tilde is sort of like the negative of that set, in that like we, take the negative of each point in that set individually, and then we get this other set. So if we're taking like H convolved with H tilde, this should just be adding like some set to the negative of that set, and then seeing like where this concentrates. Now, of course, adding a set to the negative of that set is just the same thing as taking the difference between that set and itself. So in other words, this quantity, this thing like on the inside, this H convolved with H tilde, should look like the set of all difference vectors. So here I've drawn, well, I haven't actually drawn all difference vectors because I think that there would be like, how many difference vectors? Like 78 or something. And I think I've just drawn enough to convince you that I've drawn all of them. So yeah. But we can pretend it's all of them for now. Um, and the idea is that, remember, we're taking this difference set and then we want to look at like these difference vectors and where they concentrate. So I'm going to say like for each of these differences, these are all vectors. If we want to like think of them as points, we can imagine like translating them to the origin and like looking at like where they are. So that's what I've done here. I've taken all these blue things and then I've like sort of translated them to the origin and then I put a mass on the end. And this is what we should think of as this H convolved with H tilde, or like it's sort of like a difference between two sets, right? Um, so that's like what this is about. In summary, like we looked at this difference set and we, look at all these difference vectors and we just put them here and then we put pink dots on them so that we can see them better. Okay, so then we want to like sort of step by step analyze the extra thing. So then we're going to restrict it to this and then we're going to look at L1 norms. Okay, so then first things first, if we're restricting it to like this plane, right? We can imagine like we're taking this, we're restricting it to some plane. And then we're asking for the mass. We're asking how many points lie on that plane. And if we're asking how many points lie on that plane, remember these are all differences. So if we were to ask ourselves what happens when the difference between 2 points is going to lie on a certain plane passing through the origin, that's just going to mean that the two things that we were taking the difference of sort of should lie in a plane that's parallel to like the other plane. So for example, here, like this difference here, this difference did not come from those because those two are too far away. Maybe it came from like those two. These two lie in the same hyperplane. Technically, these hyperplanes are drawn as lines because we're in 1+1 dimensions, but it's kind of hard to draw an arbitrary collection of spheres in 3-dimensional space. So I guess we'll be working with 2 dimensions. So that's sort of how we should be thinking about this, is we look at each of these slices because differences that are coming from different slices. So if we take the difference between these two here, this one is not going to lie in this new perp plane because they're coming from like these different things. On the other hand, differences that come from the same slice should give us the right differences. So I guess just to like sort of summarize that idea, the idea is that if we're taking like, we're looking at all of these points that lie on a single line and we're looking at the differences that are like going to be there, and the difference is going to lie on this line if and only if the original things come from here, because if they came from different ones, this difference is going to be like over there, which doesn't lie in this plane. Now we might formalize this as we're looking like at all of these slices, right? That age restricted to like lambda nu plus nu perp. Lambda nu plus nu perp is just some hyperplane. And we're looking for the total number of differences that are going to lie in that hyperplane. Now, as we all learned a long time ago, the set of all differences between 3 distinct, I guess, points has size 9. well, up to a constant, right? Because like, technically it should probably be like, I should be writing like n times n minus 1 over 2 or something, right? But like, um, it's gonna approach like n squared. So we can sort of imagine that we're gonna have a contribution of like 9 from over here because we'll have 9 differences between these three, and then like we have 2 things here, so we'll have a contribution of 4. On this line, we have like 4, so we'll have a contribution of like 16. So that's what we should imagine. So this equation here is telling us that we restrict ourselves to each plane, and then we look at the total amount of like mass on that plane, and we square it to get the total number of like differences that are going to come from that plane, and then we just integrate that over all planes. Okay, so if I lost you somewhere there, we can now talk a little bit more about some combinatorics related stuff. Um, if we were trying to like count the number of differences, like the number of points on each of these squared, and then like sort of sum that over all possible slices, um, then one way that we might bound that is by like, we could just bound the total number of things that are going to lie in each slice. Because remember, we're trying to give a lower bound to this because this was on the right-hand side of the conjecture. And yeah, so, one possibility is that if there were like 10 points in each of these planes, then like 10, it means there's going to be like at most like 100 in each slice, right? And then 10 is equal to 1, 100 is also equal to 1, up to a constant. And so then we can like sort of say that each slice is contributing at most like 1. And this should be like useful because like the total number of slices is going to be like around the same as the total mass of H. So in summary, we can like, if these points are like lonely and there aren't very many points in like their slice, then we should have an estimate that looks like this. Because like, I guess up to like some constant, right? That's what this means, like up at some constant. So that part is, I guess, just more combinatorics. Okay, now if I lost you somewhere there, in the end, what we did in section 4 is we bounded this thing that was on the right-hand side in terms of this. And we picked up this weird normalization factor, which if you look at it, it comes from the fact that we're like taking something that's L1 normalized in n dimensions and we restrict that to an n minus 1 dimensional space, and then it's not L1 normalized. But anyways, if we forget the normalization factors, we conclude that like if we get this estimate, then we hope that that if we get like if we have this like sort of geometric fact, then we can bound this thing. Okay. Now, if I lost you anywhere in chapters 3 or 4 or anywhere before, remember that what we were doing is that we were trying to like break our like equation into these different pieces and then analyze each one separately. And now we've done that, and I want to like sort of summarize everything that we've concluded. So in section 4, what we just did is we concluded this bound, we estimated this in terms of this, and in section 3, we estimated this using another combinatorial argument. And we can forget what star was for now. It was some weird condition that was somehow vaguely related to lattices and convolutions, but like whatever. We should be able to like write everything down and compare it at this point. So that's what we can do here. Yeah, I wrote if some magic happens, then we can like bound each of these things. So for example, like this is like the original conjecture, like or the conjecture how it was like originally stated. And in section 3, we said, okay, this thing is roughly equal to that. And then this thing of, the L theorem of F, that's a computation that I did on the previous slide, or I didn't do, but well, I guess you can do if you want to, but I don't think I want to do that computation. But we'll figure out that it's equal to this, with some normalization factor, and in section 4 we found that we can write the supremum of, like the sort of like, I want to call it the length of our weight, um, this way. And this P appeared here because, well, I can show you why. If the P was not there, then we would have a very like nice statement, but it would not actually be true because you can see that we have a factor of P squared there and a P there. So like if it's sort of like we wrote down this thing that maybe we wanted to be true, and then it's not true because we calculated it and it's not true. So we do need the extra factor of P there. And that's basically what my result is like about. Okay, so um if I lost you anywhere, basically what I found is that we can construct like a counterexample to the Mizohata-Takeuchi conjecture if some magic happens. And if you like did not appreciate any of like the computation or something like that, this is all a geometric thing. Um, we want to construct a set P and a set Q, so that both of these conditions hold. And I just written as a fact. You can find it in my paper. But basically, if P is the size log R, then we can like we can construct something that will satisfy both of these conditions. And there's a way to like verify that. I think there's a technique using like polynomials that I thought made more sense. The one that you'll find in the paper actually uses like it's purely like geometric, no analysis, because it like uses like these moment curves and these like projections. And I kind of thought that that one was like nicer just because it was like, I don't know, it was just nice how like all the projections worked out and like whatever, but maybe people have different opinions. Um, but the main idea is that we've constructed this lattice thing because if you imagine grids are nice because you can pick it up and stack it on top of itself and it like if you copy paste it, then we see these like towers like building up and like that's useful. The thing that we do not like about grids is that they usually contain a lot of lines. And right, because if you have like a 10 by 10 grid, then that's already 10 points on a line and like that's not good. So the way that I got around this is like taking a very high rank lattice. Um, you can imagine like a Hamming cube, which is like a 2 by 2 by 2 by 2 by dot 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 by 2 cube. And then we like project that down into n dimensions. And um, this is not going to have very long lines because it doesn't like have very much depth to it, sort of. But if we carefully like construct how this projection works, we can sort of ensure that like if we pick it up and stack it on top of itself, um, we'll get like at least a tenth of the points. Um, okay. Just as a side thing, this is actually like a bit of a lie that it's 10. The constant is actually 2 to the n minus 1, but 10 is equal to 1 is equal to 2 to the n minus 1 up to a constant, but maybe that constant depends on n, so we don't really care. On the other hand, this is actually like closer to a half, so we can do better than 10%. So yeah, I think that's basically, I have like one more slide about like how this relates to everything else. Okay, so this is the part where I hope I didn't get any of this wrong because there are a lot of people in the room who will not like it if I got some of this wrong. Um, okay, so the Mizohata-Takeuchi conjecture is like this thing over here. It's implied by Stein's conjecture. Stein's conjecture is sort of a reformulation of the Mizohata-Takeuchi conjecture, I want to say, except probably it came from around the same time. And like, also, if you say Stein's conjecture, people will think you mean many different things. So if you do say Stein's conjecture, you can maybe say something like weighted L2 estimate using a Kakea maximal type operator or something like that. And then that will then people might know which one you're talking about. But basically, the Mizohata-Takeuchi conjecture was motivated by the fact that, by the wave packet decomposition and the fact that the extension is to concentrate on these different tubes. And what Stein's conjecture says is that actually we can do a little bit better than that. Well, actually we can't because of this counterexample, but we hope that we could do better than that, and that we can look at each tube. Each tube has a certain amount of mass, and we can quantify how much mass is on that tube based on the specific region of the surface that it comes from. And then we look at the total amount of mass that a weight has on that tube. So instead of just going, what's the how many tubes do we have? And what's the most amount of mass we can contribute from a tube? We say, for each direction, how many tubes do we have? And what's the maximum amount of mass we can get from a single tube? And then we integrate over all possible directions. So my counterexample also shows that Stein's conjecture cannot be true, at least not without a logarithmic factor. And yeah. So how this relates to other things is Mizohata-Takeuchi conjecture is related to studying first order perturbations of the Schrödinger equation. I hope I didn't get this wrong, but I think Stein's conjecture is supposed to be related to the Bach-Norris problem. I do not study that, so that's not my area, but yeah. One reason why the Mizohata-Takeuchi conjecture is useful is because it sort of tells us that this Fourier transform is bounded by tubes, and if we can bound how tubes intersect, then we can sort of prove things like multilinear restriction using multilinear Kakea, where we can prove restriction using Kakea. And that I think was pointed out in a paper by Tony Carberry and Haninen and Boulder. I don't know their first names. And using this duality argument from I guess functional analysis. And just to sort of put into context the if you're not from this area of harmonic analysis, then you have probably still heard of the recent paper by Hong Wang and Josh Saul proving the 3D case of the Kakea set conjecture. So the Kakea set conjecture comes from sort of the Kakea maximal conjecture, and they proved the 3D case. So this is sort of I guess how it relates to I don't know, the rest of the field. Anyway, thank you for having me. I think that's everything.
Okay, let's thank Hannah for giving a very nice talk. Yeah. If I can find my react button. Okay. Are there any questions?